Recording is rolling. It is Monday, October 21st. Yeah, I got a new system here. Things been working. Gonna try. All right, so back up. Last time I saw you guys, we were putting graphs together for this centripetal force lab. Remind you guys what this looked like. Keep trying to finish this. All right, so you guys have that lab paper out. All right, so we're gonna finish the graphs on that. Finish that lab. Then have you guys turn that lab page in. On the opposite side are was another lab, right? So you guys got this page out. On the opposite side was that turntable lab, right? So when you guys turn that today, I'll give you guys two different lab grades. That'll kick off quarter two. See, AP, don't worry about that. Right. So one of the questions I threw you guys before you started this last lab was if I put some water in this cup and I whirl it in a vertical circle, the water stayed in the cup. So how was that? And then what would be the minimum speed to make sure it stayed in the cup? So we'll go back and revisit that. I have some other demos I want to do with you guys, but we'll see how much time we have. All right, there's a meteor shower going on tonight. So yeah, if you guys are watching the night sky, might see that.
What time?
Just anytime after dark. Like it's probably going on right now. You just wouldn't be able to see the meteors. Right. So yeah, it's supposed to be last night and tonight are the 2 days for the meteors. Okay, so you see the night sky? Oh, guys, tomorrow. What's going on tomorrow?
ASVAB.
That's right, ASVAB. Now, most of you guys are taking the ASVAB. You guys got phones away. You guys got phones away. You guys look up here. Think about this. So you guys probably know where you're testing. If you're testing, I've posted information on Google Classroom. You guys remember that? Okay. Now, if you're not testing, then you're going to be relocating. I put all the relocation information up there for all the classes. But here's for my class. My first 4 classes are relocated because there's ASVAB testing in this room. Okay. We got picture retakes on Friday. All right. So you guys good? Good so far? All stuff. All right. So let's go back to this lab setup right here. With this point. All right. So centripetal force. All right. We're trying to figure out. Right. So remind you guys, we're trying to figure out centripetal force. In this case, provided by this tension in the string, which is equal to this weight. Right. How much force does that have to be to keep this mass moving in a circle of this radial size at this tangential velocity, this speed? Right? There's 1, 2, 3, 4 variables right there. 1, 2, 3, 4 variables. So looks like some kind of governing equation that can tell you how things move in circles. Okay. And we're pretty close. You guys got most of the graphs done. Back last week, guess we were doing all these graphs. Now these are from different classes. Lots of different graphs over lots of different classes, but I'm just flashing them up here really fast to remind you guys what we were doing. We were labeling variable unit. You guys scaled all your axes. Notice mine are scaled with numbers. You guys also have that, right? I'm looking for all this when I'm going to grade these later. You guys plotted some points that are the coordinates, and then did some kind of curve of best fit. Right. And if it didn't linearize, then that's okay, because we're going to try to linearize all these. So far, I think you guys have these graphs done. Right. Now, all I did on this page was just do the curve of best fit. But you guys have a lot more information about. You guys did all the stuff I just showed you. You have variable unit. You guys have that for all of them so far. You guys have each axis scaled. You guys have a bunch of plots pointed. You guys did a curve of best fit, and here I've just showed you the curve of best fit. So I got what looks like probably a square root curve, and then we took each of those and we linearized them, and they look like that. Right, and then the bell rang. You guys took off for the weekend. Right, you guys remember that? Right, so we got one more lab to go, which is what is the relationship between the speed and the swinging mass? So these two variables right here. Now that's controlling for this hanging weight, right? So which is also the tension strength that was controlled. And also controlling the radial size. So I think this is the spades. Yeah, spades we're moving on to. I still had some spades last week. Feel pretty good about their data. Did you guys have spades? Maybe? Got spades, different. What did it say here? Was looking for speed and mass. Speed, mass, radius was constant. Yeah. Okay, all right, so I got some data in front of me right here. All right, so I'm just gonna copy this data. We're gonna see what this graph looks like. We're all about to find out. All right, and then put it together from here. All right, so you guys are about to make you guys see the bottom left graph, the one that says speed versus mass swinging? You guys see that one right there? Okay, we're about to make the bottom left graph. You guys ready to make it? So I'll make it with you guys, just like last week. Speed versus mass. Okay. So put speed on the vertical axis. Let's put that in meters per second. Put mass on the horizontal axis. That's going to be in grams. How do you guys do grams? 2, 3, 4, 5, 6, 7, 8, 9, 10.
Is this the V versus mass swinging?
Yeah.
Okay.
That's it. Speed versus mass swing. Okay. So 0, 2, 4, 6, 8, 10. Right there. Okay. And then mass. All right. So the largest mass on this paper was what? Okay. 156 grams, I guess. All right, let's try that. Okay. So let's do about 50, 100, 150, and then one data point's going to be just a little bit to the right of that. That'll be right. So 0, 50, 100, 150. Okay. All right, so get some points here. So see, there was 56 grams, and the corresponding speed was 5.8 meters per second. So 56, 5.8. That's right about there. I label this 56, 5.8. That's grams and meters per second. Next point, I got 108 grams and 3.93 meters per second. 108, 3.93. Okay, so that could be right here. 108, 393. This is grams and meters per second again, of course. Okay. Hey, look at that. Look, the more massive the swinging mass, you actually had to swing it slower. And I think probably a lot of you guys would have hypothesized that anyway. It's like, oh, if I make it more and more massive, I have to swing it slow, or vice versa. If I make it less massive, maybe I have to swing it faster. All right, we're already seeing that. All right, next one. I got 156 grams. That was going at 3.14 meters per second. So 156, 3.14. It's pretty close to there. 156, 3.14 grams meters per second. Okay. Right, you guys are labeling all these points. All right, we got, see, 26 grams was going at 9.85. 26, 9.85. 26, 9.85. This is grams and meters per second. Okay. And then I got 46 and 5.4. 46, 5.4. Stick right there. 46, 5.4. This is grams and meters per second. Sure. Yeah. All right. Yeah. All right. All right. So, guys got all those points. You gotta figure out what kind of relationship is that, and what do you guys think it is? It looks what? Inverse. Yeah, definitely looks a lot like that one. There's something to do with the inverse relationship. One variable gets small, the other gets big, vice versa. Okay. So here, if I do like the curve of best fit, bet the curve of best fit's gonna do something about like that. All right. How can I come up with an equation for that curve? Okay. Now, I could, well, one way you could do, I guess I could sit around and guess and check and let's say, until something fits those points pretty close, right? There are mathematical analytical techniques, and actually we're going to do something kind of closer to that, something more systematic. So, hey, I wonder if I could linearize this. Didn't we do a bunch of linearization last week too? Right? Okay. Like these are the graphs from last week. We were able to linearize these root looking curves. I bet this one's okay. It's like inverse. You guys just did that one, inverse relationship. Okay. Hey, what if we graph not v versus m, but v versus 1 over m? I bet that should linearize. You guys ready to try that? So to the right of the graph you guys just made, you guys see it says v versus 1 over m. We're about to make that graph right here. So speed versus 1 over the mass. Ooh, I wonder if this is going to linearize. If it doesn't, it should at least be closer. Speed in meters per second. I can just keep the same vertical axis as I did before. Go ahead and scale that up to maybe 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then 1 over mass. Now, this is going to be units 1 over grams. So we're definitely getting to abstract land right now. That's all right. Okay, because we can come up with an equation, hopefully. And so, what 1 over the mass? How should I scale this axis? Well, guys, what's going to be my largest and my smallest value? Like here, the largest mass was 156 grams. The smallest was 26 grams. Is what's a bigger number? 1 over 156 or 1 over 26? What's the bigger number? Yeah, 1 over 26. Yeah, right. So I'm going to do 1 over 26 in my calculator, and I'll use that to scale the whole axis system. 1 over 26, which is like 0.038. Right? So if I round up to 0.04, I could scale it like that. 0.01, 0.02, 0.03, 0.04. And now all the data for sure is going to fit right in there. 0, 0.01, 0.02, 0.03, 0.04. Okay. You guys also scale your axes. Okay. So far, this is what you got. You guys got variable unit, variable unit. You guys have your axes scaled. Got 0 to 10, 0.04. All right, you guys got all that. Now we gotta make some points and some coordinates here. I can get it based on what's already here. So, you know what? I think I'm going to do this just to save us a little bit of time. Looks like these 4 land pretty close to a curve, and this one looks like a tiny bit of an outlier. Maybe I'll skip that one. And so let's do this one. So what's 1 over 26 was, of course, 0.038. Okay. And then 9.85 meters per second. So 0.038, 9.85. That's probably pretty close to there. 0.038, 9.85. This is 1 over grams. This is meters per second. Okay. All right, next point. This one right here. Got 56, 5.8. So 1 over 56. That's like 0.018. And then 5.8. So 0.018, 5.8. So 1 over grams, meters per second. See 3.93. See 1 over 3.93. Oh, whoops, sorry. No, that's not the right one. Oops. Scratch that. Okay. Sorry, 108 grams. So 1 over 108. Okay. So that's 0.009. 0.009. And then that was 3.93 per second. 3.93. Right there. 0.009, 3.93. 1 over grams, meters per second. And this one right here, what's 1 over 156? That's 0.006 and 3.14. Zero point zero zero six 3.14. 1 over grams, meters per second. . You guys got those 4 points on your paper also? Everybody's got that. All those points. We got to figure out what kind of relationship are we looking at. So back to this set of graphs here. Which relationship do you guys think that is? Okay. Maybe linear, or here, if I go back here, let's assume for a moment if it was linear. If it was linear, okay, I could hold my ruler up there and get okay, a line best fit, and then guys, look at this huge y-intercept. If that y-intercept was true, what would that point represent? Right? This is one of the things I want you guys to, of course, get out of this class is this kind of graph interpretation. Like, well, what would that point really mean? Well, I mean, if you did 1 over the mass and got to 0, which would mean the mass itself would be extremely what? Extremely small or extremely large? Large. Yeah, like if you had like 5 tons or something. Guys, 1 over 5 tons, that's getting pretty close to 0, right? So if I had like a 5-ton mass I was swinging around, right? That if this was a linear relationship, then that would mean I'd have to speed, about 2 or 3 meters per second. Because does that sound about right? I got like a 5-ton truck and I'm just swinging around about 3 meters per second. Does that sound about right? No. I think how about 0, 0? Do you guys think 0, 0 makes a lot more sense? I think that would make a lot more sense, right? So I think what you're actually looking at is just this part of a root graph. Guys, doesn't that part of a root graph right there look pretty linear? Especially if you just have a handful of points. I think that's right. You might think it was linear, right? I think that's what it is. So here's what curve I think we're actually looking at. There's something a lot more like that, right, where it kind of curves down. Okay. So I suspect that the speed is proportional to not 1 over the mass, that would have been linear or a direct relationship, but the square root of that. Doesn't this look like y equals the square root of x? Probably, okay, something like that. Okay. Now, if that's true, we're about to make one more graph. There's still one more graph you guys got to make, and I'll make it with you guys. Okay. I could graph v versus 1 over m, and if my hunch is true that that's proportional, then this should linearize into a true straight line and it should go through the origin, like a direct relationship. Okay. Alternatively, you could square both sides of this proportionality and say v squared is proportional to, and then square the square root, that goes away, 1 over m. I put this little cloud bubble here. Because those are saying the same thing. And if one's true, the other is also true. They're the same thing. Okay. Now, the reason I like the bottom version, v squared proportional to 1 over m, is because the graphs that you made so far on the right side are all v squared is proportional to something. V squared was proportional to the weight back last week. V squared was proportional to the radius last week. Right? And now we've got one more to go. And it's v squared versus, look at that. V squared versus 1 over the mass. This should line up in a straight line. Okay? You guys ready to see if it does? Yes. Oh, yeah. We are ready. So, one last graph. All right, you guys got some axes already. I printed those for you. We're doing v squared versus 1 over the mass. You guys got the title written. Okay. All right. Now, time to write some stuff. Let's do v squared. This could be in meters squared per second squared on the vertical axis. So everybody just write that variable unit. Then on the horizontal axis, I'll do 1 over the mass. That's going to be in unit 1 over grams. You guys just wrote that on your horizontal axis, variable unit. You guys got that? Okay. Actually, that axis I can scale exactly the same as right here because I already got that. I already scaled up to 0.04. Okay. So just copy paste that right here. So 0, 0 0.01, 0.02, 0.03, 0.04. Boom. Right, then the speed squared. Let's see, what can I do with that? Okay, well, I can just take all these speeds that I already have and just square them one at a time. See what happens. So let's do it. Let's take like 3.14 and I square that. That's going to be 9.9. I'll call it 9.9. Okay. So Whoops. Sorry, I gotta scale this. Oops, I forgot to scale it. Let me pick my biggest number. My biggest speed was 9.85 meters per second. Square that. You're gonna give me 97. That's almost 100. So maybe I should scale this entire vertical axis up to 100. I think that would be perfect. So 20, 40, 60, 80, 100. So 0, 20, 40, 60, 80, 100. All right, so now all my data is going to fit in that space right there. So now I can do the 3.14 squared is about 9.9. Right, now I have a space to put that. So there's 6 here, 9.9. It's like right, bam, right there. So there's a point on the board. Plus 0.006, 9.9. Okay. Now we've got really weird units on these numbers, of course. This is 0.006, that's 1 over grams, and 9.9, that's meters squared per second squared. Right, so these are definitely abstract. Okay. But if these all linearize, if all these points linearize, then we can come up with an equation real easy. All right, next one. All right, how about this one? So it's 3.93 squared. 3.93 squared. That's like 15.4. Right, so 0.009, 15.4, 15.4. That's right about there. 0.009, 15.4. All right, next one. Let's see, 5.8. What happens if I square that? 5.8 squared is 33.6. So 18, 33.6, 0.018, 33.6. Okay. And last one, the speed was 9.85 meters per second. Square that, I'm getting 97.0. Yeah, that was at 0.038. 1 over grams. 97 is way up here. It's probably about right there is what that is. Okay. So 0.038, that's 1 over grams. And 97, that's meters squared per second squared. Okay. Okay. All right, so on your last graph, the one in the middle on the right side, you guys got those coordinates also plotted. Of course, you have you guys on your paper should have everything that I just wrote. Okay, so you guys have everything that I have? Okay, it's all good. Okay. And oh, look at this. Line of best fit. That actually does look a lot more linear. Okay. Yeah, that's really close to being linear right there. So let's call that linear. Okay. Go one more step. If I want to know what is the equation of that line, okay. Now what the important takeaway at this point is that b squared is proportional to 1 over n. But if I want an equation, let me show you guys you can get an equation. And that's a good thing you can do with linearization anyway. I can just pick 2 points on the line and do rise over run. So how about, here, I'll pick the origin. This point says you've got this going through the origin. And how about this point right here? What is that? That's about 70, maybe I'll call that. Okay. So this is 0.0370. Let's see if I divide those, rise over run. So let's 70 divided by 0.03. So this rise divided by this run. You guys see I'm getting the slope of this line? Doing this, I picked a point on the line, did this rise divided by this run, rise over run. So if I'm walking uphill, how steep is this hill? It is, it's got a slope of 2,333. I'll round that to 2,300. Only 2 digits anyway. So I can say this, speed squared, which is the vertical axis, looks like my y-axis. So instead of saying y equals, I can say v squared equals. Now I can make a true equal sign. I've just been doing proportions all along. But now I'm going to throw in an equal sign. This number, 2,300. Now this number has units. It's also rise over run. The rise was in meters squared per second squared. The run was in 1 over grams. So this is a really weird, funky unit. I'm sure you can clean that up, but I'm just going to leave it like that. Times 1 over the mass. Okay, this right here is the equation of that straight line. And it's also the equation of the last 2 graphs also. Like this graph, here, let me point them out. Right, this graph you guys just made and these 2 graphs over here. Actually, we have this drawn in. Where did I put that? Thought I had it right over here somewhere. Well, anyway, so you guys just drew those graphs. This equation could describe all those graphs. It's all the same graph, right? And here's what this could be, because guys, there's like 20 different students in here. You guys gonna have like 20 different careers and 20 different life stories. You're gonna see a lot of graphs and a lot of equations in your life somewhere, regardless of what that is. You're gonna have to interpret, like, what is this equation telling me? So suppose you saw something like this, right, where you saw like real abstract, because I want you guys to pick up these skills out of this class, so you know how to interpret equations, interpret graphs. Right? If you have the paper that I got this from, you have some weight that was hanging, some tension force, and you also got some radial size locked in. So those are the controls. Let's say you're switching out the top canister, so different masses that are swinging around. And you want to know, hey, how fast do I have to spin it? Given those other control variables, right? Suppose you pick up that particular equipment. I can say, oh, well, whatever the top canister is, just do 1 over that. That could be in grams. Multiply that by 2,300. Okay? They'll tell you your v squared. So the last thing you do is take the square root of both sides. They'll tell you the speed, v. That's exactly how fast you should spin that. Okay? You guys see that? Okay. So, to here's what I'm looking for. Right. I was looking for that was somewhere nearby. Right. So I drew in the last few. So we got an inverse, we got another square root, and we got that linear relationship right there. Okay. All right. Do you guys see at the bottom? There's a couple of tiny boxes. All right. So one says, how are the centripetal force, the mass, the speed, and the radius related? And they set up v squared is proportional to. And there's another box, but let's see this one first. So these 3 graphs right here, these 3 linear relationships are saying this. I got the speed squared is proportional to the weight hanging, which is the force in general, which is also the tension force. They're all the same force. They'll say force, centripetal force. The middle graph that we just made says v squared is proportional to 1 over the mass swinging. And this third one at the bottom, which we also put together back on Friday, says the speed squared is proportional to the radial size, right? So all these things are individually true. Now that came from 3 different type experiments with three different groups, right? You guys were with all different controlling different variables, right? But hey, look at this. Speed squared is proportional to this and also this and also this. Guys, can I just mash that all into one giant master equation? Or proportionality, I guess at this point. It'll look like this. Speed squared is proportional to, set up a fraction bar. Guys, go ahead and fill in that fraction before I do. See if you can do it. I bet you can do it. Can you guys write that fraction? Speed squared proportional to the centripetal force, F.
F times R
Uh-huh.
over M.
That's it. FR over M. Yeah. So no, that's a proportionality. Okay. That is the answer to this box right here. Right. It used to use different proportional symbol. That's why it looks a little different. Okay. Yeah, FR over M. Okay. There's still one more thing we gotta do here. Here's what I'm looking for. Okay. So go back to this. Guys, this poster is titled Centripetal Force. So, I wonder if you could solve for what is this force, like this tension force, as a function of mv and r, right? Like the perspective, we're trying to build an equation from the perspective of if you're given the swinging mass and you know how fast you're swinging it and what's the radial size, can you determine what force is holding it in a circle, right? Well, we got all the parts lying around right here. We just got to rearrange this and solve for this centripetal force. And this would represent the centripetal force, wouldn't it? Right? Can you do that? So here's the next line. Force is proportional to, set up a new fraction bar. Can you guys do a little algebra switch around and solve for that? Go ahead. See if you can do it before I show it. A couple algebra steps. Nothing crazy, nothing we haven't done so far. And what did you guys get?
Or then you
Exactly, mv squared over r. You take this m, cross multiply it, that gives you mv squared. And then take this r, divide it down. Yeah, mv squared over r. That's it. Now at this point, I'm saying a proportionality. Right. Oh, but let's say you want to make this an exact equation, right? Okay. So, guys, if this was an equation, do you think there might possibly be a coefficient in front? Right, and that coefficient might have a number. It might have units attached, maybe. Right. Let's think about units for a minute. If there was a coefficient in front of this to make this an exact equation, what units would it have? So what units are already lying around on the board? Because what's force measured in? Let's go back to just base SI units, because if you pick up a textbook, probably everything's in, base SI units. So guys, what's the base SI unit for force? Newton? Put newtons as a unit. What's mass measured in? I had you guys use grams, but in general, like in a textbook, it's what?
Yeah.
Kilograms? Right, kilograms? Right. What's speed measured in? Meters per second, right? Like miles per hour, but we use meters per second, right? Now let's be in squared. So I'm going to go ahead and do this. I'm going to go meters squared per second squared. True? You know that? Right? And then divide by, and what's radius measured in? Meters, right? Ooh, look at this. There's one of the meters goes away, right? That leaves you with kilogram meter per second squared. So that's kilogram meter per second squared. Hey, guys, kilogram meter per second squared. There's a name for that consolidated unit. What's that called?
velocity, acceleration, something, speed.
Oh. Here. Guys, kilograms measures what again?
Mass.
Mass. What does meters per second squared measure? Acceleration. What is equal to mass times acceleration? Newton's second law of motion. Second law of motion. F equals ma. F equals ma. Right? And what's force measured in? Newtons. Hey, look, guys, this is already 1 Newton. Guys, 1 Newton is 1 kilogram meter per second squared. It's the same thing. Okay, you guys said 1 Newton is 1 kilogram meter per second squared. And if you forgot that, just think about Newton's second law of motion, which is right here. Right? So masses in kilograms, accelerations meters per second squared. Okay. So, for example, if you kick a soccer ball with so many newtons of force, and you know the mass of the soccer ball, you can calculate the acceleration while you're kicking it. Or you guys remember that? That's just a review from a few weeks ago. Okay. Right. So, but let's get back to this then. So if we want to construct an equation and think, okay, well, we might need a coefficient. What units would the coefficient have? Well, you don't need any units because they're all already there. Right. Okay. So maybe I need a number possibly. You know, maybe like, well, I don't know, do I need a 1/2 coefficient or something like that? Right. Now, you can look at your own data because everybody has data. Now you're controlling different variables, changing different variables. That's okay. Because I bet if you change this proportional to a straight up equal sign, I bet it's going to land pretty close. Go ahead, pick any row from your data. Say, what mass did I use? What speed ended up coming out? What radial size to do mv squared over r? I bet it's not going to be too far off from the weight of the hanging canister. Okay. You guys should try that. So that's the full equation right there. All right, and that is the rest of this poster that I hadn't revealed yet. All right, so back to this. Get this right here. Let me get my. That goes here. All right, so what are we looking at? All right, so here's the answer. Centripetal force, in this case provided by the tension in the string, is equal to mv squared over r. That's it. Right. So remember, the mass is the one swinging around. Right. So I know the swing mass on this curved path. I know how fast it's going. I know the radius of curvature. Right. This will tell me what does the tension force have to be. Okay. Better. Right. Oh, and how again do you go from mass to acceleration? Here, where we just talked about Newton's second law of motion. This is Newton's second law of motion. Okay. Guys, if you know the force and you want the acceleration, I kick a soccer ball with so much force. I wonder how much it's accelerating. I would have to know the what? the mass of the soccer ball, and then just divide that down. Isn't that true? Force divided by mass. You see it? Right. Here's what I want you guys to see. Back over here. These two boxes, if you know one, you can know the other. Like, another thing I want you guys to get out of this class is that you don't necessarily have to memorize a bajillion different things. If you just know a handful of things and you know how things work, you can figure out everything else. So if you know mv squared over r is equal to centripetal force, and you also know Newton's second law of motion, guys, look at that. Centripetal acceleration, like if you were a ladybug that landed on this top mass and swing, how many G's do you feel from swinging around like that? Right? That's what this bottom one says. It's just v squared over r. You just divide through by the mass. Right? So it doesn't matter how massive it is. Okay. Like I said, like if you're a ladybug and then like a mosquito, you got different masses, right? You're like, you both feel like the same G's, right? The same acceleration, centripetal acceleration. That's what that is. Right? All right. I should show you guys. Well, let's do a couple other things, right? So one's a little bit more nuanced. Oh, yeah, isn't it true that we've been assuming this whole time that the string is pretty much exactly horizontal? But I don't think that's 100% true. Like, especially if you swing it kind of slow or use kind of a large swinging mass. Do you guys think this is a bit more realistic, what I could call a conical pendulum, or something like that? Like it wasn't straight horizontal. Realistically, it would hang kind of down. Now, if you were either using a tiny mass or swing it pretty fast, it'd be close enough to this that all the lab data is plenty good enough. You don't really have to worry about it, right? But I did want to give you guys the more nuanced version of this, right? And let's think how this would work out. So if this is like a conical pendulum, that this mass really does have some weight that we've been ignoring the last few days, but it does have some weight, right? That's going to be significant, especially if it's swinging kind of slow, right? Then the tension's pulling off at some angle. Hey, if you know this angle, which is no longer 90 degrees, somewhere between 0 and 90 degrees, you could do some trigonometry and say, how much is this tension holding up? And how much is this tension pulling this mass in, like acting as the centripetal force? Ooh, right. And we got it right here. So in the vertical direction, hold on, let me hit pause real fast. All right, so this tension is now doing two things. It's holding this mass up with a force equal to its own weight. Wouldn't that be this tension force times cosine of this angle? That's what this says right here. Tension force times cosine of the angle, right? Minus this weight zeroes out, so that this object's not moving up or down, right? Now, there is a net force pulling in. That's the centripetal force. That's this bit right here. So that's the sine component of this tension force. If you're playing off the angle from the vertical, there'll be a sine component. Okay, that's equal to the net force. And the net force is the centripetal force. Hey, look at that. So that's all right there. There's a little more nuanced take right there. Okay. I should tell you guys, if you're keeping track of accelerations, you've really seen at this point in the class 3 different types of acceleration. Okay, you guys got that? 3. And there are different concepts with different units. So let's do a review. The first type of acceleration that you learned is what right now I'm calling tangential acceleration, or you could just say linear acceleration. Remember I taught it this way? It's the rate change of velocity. So if you're in a car, you're speeding up or slowing down. Right? Okay, so that could be like this, right? Change of velocity over change of time. On a turntable, that'd be like, or if it was a giant circular track, you could imagine, even if you're turning the steering wheel, regardless of that, you could be hitting the gas pedal or the brake, right? And changing your velocity in a linear type sense. Okay. Right. Then last week, you guys remember doing the turntable lab? We were talking about, well, for a whole turntable, the turntable itself could be speeding up or slowing down. I've got a new character, alpha, this Greek letter alpha, to designate something called angular acceleration. Could this be in radians per second squared? Okay, so it's still speeding up and slowing down, but now it's in a turntable sense, okay? Like a rotational sense, okay? Now, today, we're adding a third type of acceleration. This is centripetal acceleration. Guys, which direction does centripetal force always pull? Towards the inside of a circle, right? Right? Either pull or push, depending if you have how you get that force. Right? Hey, look, that's also the direction of the centripetal acceleration. So if you're like a kid riding a merry-go-round, right, and you're like hold on to the handlebars, those handlebars could be like pushing you always towards the center. Look at that, right? Now, this would also have unit of meter per second squared, kind of like the tangential acceleration does, but it's a different direction with the different type concept. Okay? Okay, different direction. Okay, so we got tangent to the motion for A, tangential. We got in the direction of the rotation with angular acceleration. We got always directed towards the center for centripetal acceleration. Okay, guys got those? Okay. All right, I think we're ready to tackle the question from a few days ago. All right, do you guys remember this cup? Cup with some water. Let's get some water back in here. Get some water. Okay, so now I got some water in the cup. You guys see this water in this cup?
Water. Oh.
Okay. You guys remember last week? I said, how can I turn this upside down without the water getting all over my floor? You guys said, oh, you just spin in a vertical circle. Right? That's what you guys said last week. I'm doing that right now. If you're watching this video at home, imagine that. Vertical circle. And then what if we do a little slower, and a little slower, and a little slower? You guys think at some point it's going to be too slow and the water actually will fall out? What is the minimum speed to keep this water in this cup so that while it's upside down, the water still doesn't fall out? All right. And I think since you guys know this, since you guys just derived all the equations for this, I think we're ready to answer that question. Actually, I'm gonna maybe cheat a little bit. I'm gonna play off a poster because I do have a poster for this, which is probably already also in your notes, your thumbnail notes, right? So let's play off this. Okay, so say I got okay, so here's my cup of water. It's upside down at this point. Look, see, like upside down. Can you guys imagine this could be a cup of water upside down, right? Or just change out the story if you want. Hey, could this also be maybe a roller coaster loop? You're like going upside down a roller coaster. I hope I don't fall out of my seat. How fast do I have to go? I learned it in physics. It was October 18th. I remember somehow. So if you do a free body diagram at this point, see what forces could be acting. Right? Well, you got the weight. The weight's trying to pull you down. Right? So mg. Of course, if that wasn't true, you wouldn't have to worry about the water flowing out at all. Right? Also, some force in addition to that. If it's a cup on a string, you're thinking from the cup's point of view, maybe you could call it the tension in the string. That's what I put on this poster. Right? If you're thinking from the water's point of view, if you have water in a cup, it could be the normal force of the bottom of the cup holding it in. Right? But it's some kind of downward acting force. Right? And then okay, there's some tangential speed here, so v. So I'm going around. Right? We're really just focused on that top picture, right? That's the point that if the water was going to fall out, it would fall out at the top, right? So I'm definitely going to focus on that. Okay, right. So let's get some equation going. I could say this. I can say the net force at the top is the sum of these two different forces, right? The weight itself and what other additional forces holding it down, whether a tension of a string or the normal force on the bottom of the cup, however. Okay. Okay. Now, guys, what if I swing it a little bit slower, a little bit slower, a little bit slower? Is the weight changing? No, the weight doesn't change. Right? What about this additional force? Might be tension, might be a normal force. If I swing it slower, 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 what's happening to this other force? It's getting what? Smaller and smaller and smaller. In fact, what if I go slow, slow, slower? It just barely gets around. What if you were a fish swimming around inside the water? Would you feel maybe weightless just briefly? Right? And what do you think? What value, what number do you think this force approaches? 0. Right, so that's going to be, that's why I crossed it out here. Right now, and for net force, you guys see the net force would be the centripetal force. Centripetal force might be a force, might be a combination of forces. Here I have is a combination of forces, except I'm letting one of them go to 0. Right, so now the centripetal force keeping, in this case, maybe the water in the cup on this curved path would be provided only by its weight at that very instant, okay? Because the other one just goes to 0. Okay, you guys see that? Right? Ooh, guys, what cancels out on both sides? What cancels out? The mass. The mass. Okay, now think, what does that mean? Right? One thing I want you guys to get out of this class, what does that mean for something you cancel out? Because what if I put in just a little bit of water, and then I like double the amount of water, and then I triple the amount of water? Does it matter how much water is in the cup? No, because the mass cancels out. Right? I mean, unless it like changed the radial size a little bit, but let's ignore that. Yeah, it doesn't matter how massive is the water in the cup because the mass cancels out right here. Okay? Let's say you want to solve for the speed v. Right? Guys, can you solve for the speed v? Can you see it? You have some notes out, maybe some scrap paper? Okay. I'll have to show you guys because we're getting pretty close to the bell. Okay. But guys, this is how it finishes out. I know this is in terms of variables, but maybe if this showed up as a quiz question, then you guys have the answers to everybody's quiz. Different masses of water, it doesn't matter. Different radial sizes, you just plug it in here. I could even switch planets, and you can just also plug that into that equation. That's the answer right there. Square root GR. That's the minimum speed to guarantee it gets around. All right, guys, turn in your double lab paper into that gray tray. That'll be the first 2 grades on quarter 2.